Hey, and welcome to another data science project here on the channel. Today's gonna be a fun one because we're gonna be taking a look at the Digit Recognizer project here on Kaggle. Now, this is gonna be based off of the MNIST dataset, and there's a few different ways that we can approach this problem. Now, I'm gonna throw this in my PyTorch series, and this is gonna be the last video, at least for now, within that development block of videos. But the best part is everything I cover in this video with code is going to be covered in other PyTorch videos. So if something doesn't make sense, just pause the video, watch another video that I have in this PyTorch playlist, and go back to this. Although I will try my best to explain every single line of code that I am writing. Now, my score on this, I ended up getting about 99%, which is pretty good. It's not perfect by any means. Could I have gotten a better model if I spent more days working on it or even more hours? Yes, but there's a few other projects that I want to start taking a look at, and I would see marginal benefits at that point, especially with this 99% accuracy. So with that being said, I'm going to start coding. I do have the notebook also down below, so feel free to copy it, use it for practice. And if you do enjoy these videos like this, make sure to subscribe to the channel because I'm developing at least 2 to 3 videos every single week focused around data. All right, let's start coding. All right, guys, so here we have the Kaggle competition. So just go to kaggle.com/competitions/digit recognizer, and it says learn computer vision fundamentals with the famous MNIST data. All right, so type that in or click the link down below in the description. Or if you're in the Kaggle Discord, pretty easy to find this itself, which I have a Discord group. All right, so let's just start here. If you have some experience in R, Python, or machine learning basics, which should most of you guys if you're following this channel, or even the PyTorch or machine learning playlists that I have over here, new to computer vision. So it talks a little bit about MNIST, right? It's the Hello World data set of computer vision, started in 1999 over here. And we're taking a look at 10,000 or tens of thousands of handwritten images, which is essentially this over here. We're actually going to plot one of these as well. And just continue to go through, right? Practice skills over here. And there's quite a few different ways that you could solve this, although we're going to be using PyTorch specifically on it. And we go over here to the data on here, talks about the train and test CSVs. Each image is 28 by 28, 784. That's important. Also over here, the pixel value is integer between 0 and 255, 785 columns, right? A little bit more information. And that being said, let's start coding. So all you have to do, you go over here to code, you click a new notebook, and Kaggle will get a bunch of stuff ready for you in the background. Now you see over here input, right? Digit recognizer. We have our testing and our training CSV. We have our outputs over here, which we have nothing there yet. So I don't need this cell. We're going to create a new cell like that. I actually built out quite a few of these. But before we even really start, click these 3 dots over here. We're going to go to an accelerator. So I'm going to say use the GPU T4 times 2. And it talks about improving image processing and neural networks. We're dealing with that in this video. So make sure to turn that on. And let's start coding. So first thing that we're going to do is we're going to import in quite a few libraries. So let's get going with that. Import torch, import in torch.nn as nn, import torch.optim as optim, import torch vision, then import torch vision.transforms as transforms from torch.utils.data. We're going to import in our data loader, which should be capital L, and dataset, then import matplotlib.pyplot as plt, import numpy as np, import pandas as pd. And that should be everything that we're going to import in this video. I just wanted to put this over here. Maximum interactive, stop running one of your GPUs. Oh, that's because my other one over here. All right. Now we're going to write device agnostic code. So that way, if you do have to run this on a CPU, it still runs. So we're going to say device equals torch.device. We're going to say over here, CUDA, if torch is available. Great. And then you're going to say else, throw in your CPU over here. Great. And just run that. Shouldn't have that error anymore. I just turned off the other device. And then we're going to print out our device in a second too. So I'm just going to say print device so we can see specifically what we're running on over here. And while this is still running on here, let's build out our custom data set. So here's how we're going to do it. We're going to say class, and we're going to say custom MNIST data set, and we're going to throw in a data set in here. All right. So now what we're going to do is we're going to create our dunder init method over here. So we're going to say init. Now, all these are always going to need a self. This time we're going to bring in a CSV file because that's what we're getting supplied, right? Then we're going to say transform equals none, capital N. And then we're going to have something for is test. This is something I had to add in at the very end just because of our test data set. And I'm going to say is false on this one. And then we're going to say self.data frame is going to be equal to pd.read CSV. And we're going to put our CSV file here specifically. Right. Then we're going to say self.transform equals transform, and then self is underscore test equal is test, right? So that's going to be our init. Then what I'm going to do is our length or len. So again, special over here, we're going to do len. Throw in yourself, which is always that specific instance. And what we're going to say is return, we're going to len our self dot data frame. Okay. Now we're going to do our get item, which is the third method that we need. So get item like that. Then self, throw in your index like that. All right. Then here how we're going to write this out. We're going to say item equals self dot data frame. We're going to say iloc over here. We're going to throw in our index. I changed up the code a little bit because I did get an error message that what I had earlier was going to be depreciated. So that's why we're going to be using iloc on here. Then we're going to say if self dot is test. I'm going to say image equals item dot values dot reshape. We're going to reshape this to 28 by 28. Make sure this works. Then we're going to say as type, and we're going to hit np.uint 8. And that's going to go from 0 to 255 that we talked about. It's an 8-bit integer, right? And then we're going to say label equals none. And the reason why we're doing that is in our test data set, there's going to be no labels, right? So make sure we put that there. Then we're going to have an else statement. We're going to say else. And essentially what we're going to do is we're going to copy this. We're going to make a few modifications, but we're going to copy this over here. And we're going to say item over here is going to be 1. And we're going to say over here like this. Okay. That value is reshape. All this is going to be the same. And then for our label, we're going to say item.iloc. And we'll put 0 like this. Now, what we're going to do is we're going to say image equals to transform like this. So transforms, I should say, to PIL image, and then image here. Okay. And then a few more lines. So we're going to say if self.transform is not none, image equals self.transform And we're going to do other transforms. Just easier in the code if we put this 2pil image over here. And then what we're going to say is if self.isTest, say return image, else, and I forgot the colon, but let's put that there, and say return image and label. So let me make sure this code is correct over here. So class custom MNIST dataset def init with self CSV transform none test right false data read or pd.read CSV transform self test return length self.data frame get item self under index item equals self.data ilock index self test is none image over here, right? There's gonna be no label associated with it. That's what we're gonna throw at the very end to see how accurate everything is. Else we have our image, right? Everything from 1 greater on, because they mentioned, at least in the beginning, our label is gonna be that first specific column. So that's why we have this ilock 0 over here. Then we're gonna transform this over here, self not none, image self transform. Yeah, I think this should be good here. And we're still having this cap over here for some reason. I did change that. I'm just going to put an accelerator none, so that way we don't get more errors. I'm just going to rerun these real quick. So I'm going to run all, and I do apologize for that. All right, so I'm going to have a few more lines of code we're going to build out. Next, what we're going to do is build out our transform. And I should mention, if you guys only have one Jupyter notebook up and you click these 3 dots, it should work perfectly fine for you. Okay. So what we're going to do is set up our transform. So transform equals transforms dot compose, and we're going to compose multiple transforms together. So let's do that over here. And the first transform we're going to do is a random rotation. So we're going to say transforms dot random rotation like this. Okay. And you can set the degree amount. I'm going to say 15 specifically. I found that worked pretty well. I changed a few different values testing. Then we're going to say transforms dot toTensor. Okay. And then one other thing that's pretty popular to do is normalize your value. So transforms dot normalize, and we're going to set this up. The first one we're going to do is 0.5 comma, and then over here 0.5. And you'll see a lot of normalization within PyTorch. Okay. And for an R on that one, we should be fine after that. And we are. Let me just make sure we're also on our CPU. Yeah, so we're on our CPU. It's not a big deal. I'll just cut out once we start running the model because it is going to take a little bit. It took a while also on my GPU when I was running it. All right. Now what we're going to do is set up our train and test data sets. So let's do this together. We're going to say train data set equals, and essentially what we're going to do is we're going to go back to this custom MNIST data set. So put that in here. We're going to also have our CSV file as our first input. Again, why we're doing that is we put our CSV file here. So we have to call our CSV file transform and then also is test when we're creating these train data sets. So what I'm doing is CSV file, it's going to be equal to, and what you can do is go over here and you can copy this file path and then throw it in here over here. So that's my train, right? And then I'm going to say transform equals transform. And then we're going to say is test equals false. Now what I'm going to do is copy all this, right? Now we're going to say our test data set, and we're going to say is test equals true this time. And we're going to change up this URL. We're going to copy this test one, which essentially, honestly, you could just change this to test.csv. So the fireworks are pretty loud outside right now. So again, I do apologize if you hear that. Someone is having a fireworks show nearby. But this will be running over here. And once this is done, I want to show you a few different things we can do over here with our data sizes. So we can say print, and what we're going to do is say our train size is like this, and just write out a quick print statement. We're going to say string, we're going to say length, train dataset like that. All right, so then we're going to do a plus over here. We're going to say test size. And we're going to do a plus. And then essentially I'm just going to copy this code over here and do this for the test. Just to show you guys this class we created worked properly. And hopefully it did. So we see a train size 42,000, a test size of 28,000. So that does look correct. And also what I would like to say as well is we can just go over here, train data set, and I'm just going to put 1 over here, right? And you can see this tensor that has been printed out right over here, and quite a lot going on. All right, so now let's build out our data loader. So let's do that. First thing we're going to do is set up our batch size. We're going to say our batch size is equal to 64. Then we're going to copy a lot of the code for train and test data loaders, but what I'm going to say is train data loader over here. It's going to be equal to torch.utils.data loader like this. Our data set is going to be equal to this train data set. Then our batch size equals our batch size that we called, right? So batch size equals batch size. Then we can shuffle this. So I'm going to say shuffle equals true. And lastly, num workers. I would just put 2 over here. So just say 2. What I'm going to do is copy this code because I don't like typing out twice. We can say test this time and everything else should be the same, right? So now we can run that over here. No problem. And all right, so now we're going to print out an image. And I can't remember where I originally grabbed this source code from, if it was ChatGPT or if I read it from an article or something like that. So I can't remember that reference. But here's how you can do it. You can say, for example, data, and we're going to say example labels in train. You put loader like this. All right. Now what we're going to say is we're going to say example image equals example data. Grab the first thing over here, and we're going to say print. We're going to print out our input size, and then what we're going to do is example data dot size like that. It's going to print out our size. We'll need that a little bit later. Then we're going to say example image numpy equals example image permute. And we just got to rearrange these different channels. Essentially what we're doing is converting a PyTorch tensor to a NumPy array with this over here. So NumPy makes it easier to print. We're going to say plt.im_show. Then we're going to put this example image NumPy in over here. Then what I can say is plt.title. And then all we're going to say is F. We're going to say label like this. Then inside over here, we're going to say example label. And we'll put over here a 0. And then what I'm going to do also is plt.show. And lastly, we are going to break. And I think that should be correct. Do have a small error. So I am having an error over here. It says too many values to unpack. I'm going to debug this. I did notice real quick. This shuffle over here needs to be changed. And we need to put a test loader over here. I forgot to change those out. So that should fix that. And that does fix this down below. So do apologize for that mistake. But make sure you put shuffle as false. And you actually make this as your test loader, not train loader twice. And you can see this example 9, right? So this is 9, what it looks like. Do another one over here. 6, we have 6. We run it again, 8, and we have an 8 down below. All right, so now let's work on our specific CNN module. So this is going to be probably the most complicated part of this video. I do expect myself to make a mistake or two. So let's get going. So we're going to say class. We're going to say simple CNN. We're going to put nn.module over here. Okay. So let's put that in. All right. Then we're going to say def init. Put our self like that. And we're going to super over here. And that super, we're going to put in our simple CNN. We're going to say self. And then we're going to do dot init like that. All right. So now what we're going to have to do is create all our different layers over here. We're going to start off with a convolutional over here. So self.conv1. And I think we're going to end up creating 3 over here if I remember correctly. So we're going to say nn.conv2d. First thing that we're going to do is set our in channels. Now, it's only one color, so we're going to say in channels equals 1 over here. We're going to put out channels to 32 equal 32. We'll set a kernel size equal to 3. Then we're going to say stride equals to 1. And lastly, padding equals to 1 as well. Then we're going to do a reloop. So add some non-linearity over here. And that's going to be equal to nn.relu like that. Okay. Then we're going to do a pool. So self.pool. That's going to be equal to nn.max pool to d like that. We're going to say a kernel underscore size equals to 2. Our stride equals 2 as well. Then what I'm going to do, I'm just going to copy this and we're going to create 2 more of these over here. We're going to say 2 and 3. We're going to change up a few things, but some of the code's going to be the same. So first, what we're going to do is in channels is 32, right? So our out channels for our first one was 32, so that's why we're doing 32 here. We're going to change this one over here to 64. Then down below, we're going to have 64 to 128. All right. And everything else is going to stay the same, right? 311, 311. And then what we're going to do is have a few more lines of code before we get into our forward method. So we're going to say self.fc1 equals nn.linear. And then I'll show you where we get these numbers for in a second. And 128. Then we're going to do a dropout equals nn.dropout 0.5. This layer essentially helps stop overfitting within our data. We're going to do fc2 equals nn.linear and do 128.20 and then self.fc3. We'll throw 20 in here and 10 because it's our final side of things, right? 10 digits. And how we got this 128.77. So essentially our out channels over here for layer 3 on here, this convolutional, once we get 128 and 7. Let me do some math for you guys. So there's this formula out over here, and we'll go through it a little bit. So width minus kernel plus 2 times padding divided by stride plus 1. So essentially what we do is we have this for our first one, right? 28. We get the width over here. It says 28. Also told you in the description, said in the beginning. So we do this math, right? And you're going to get over here 28. But then we have to divide this by 2, which gets 14. So just to show you an example, right? 2 times 1, right? So we have 2 times the padding. Our padding's 1. So that's 2 over there. Our width is 28. Our kernel's 3. So 25 plus 2, 27 divided by 1, right? 27 plus 1 is 28. Then we get into this pooling layer over here. Pooling will divide by 2. So we're down to 14. Then we throw this in over here again. So this time, same thing, but we have 14. So 14 minus 3, it's going to be 11, plus 2, 13, plus 1, right? Or we're going to divide by a stride, which is 1. So we're at 14 again, right? Go through it again. And we have another pool, so we divide by 2. So that's where we get these 7s for on here. So now what we can do is build out our forward function or forward method. So we're going to put our forward over here. We're going to say self and also X. And you can either put all these in like one specific line, or I shouldn't say all these, but most of these in one line, or you can write them out. Sometimes I prefer writing these out because you can see what's going on, but it is going to be a bit tedious, so I do apologize. So with conv1 over here, X, essentially we're going through all these layers again. I'm just going to build out a bunch of these, and we're just going to go through. So relu, then over after the relu, we have our pool. Then after our pool, we have convolutional 2. Then we can put another like relu over here. And then we have our convolutional 3. And then our pool again. Okay. Then we're going to set our size. So X size like this equals X dot size 1 times X size 2. I'm going to do this again. X dot size of 3. We're going to say X equals X dot view -1 X size like that. And then we're going to do these layers essentially, right? So X equals, and then self FC1 like that. Throw our X in here. And do another relu. You don't always have to have your relus in here. You can bring it down below. And we'll do 2 and 3 also. So just copy that. Right. 2 and 3. And at the very end, we'll return our X. Okay. Now, hopefully we have no errors there. I mean, we'll see it in our training or testing loops. If we do. But now, let's initiate our model. So model equals simple CNN to throw a device in here. Criterion, we're doing cross entropy loss, nn.cross entropy loss, especially since the classification problem. Optimizer equals optim .sgd. Then over here we're going to say model.parameters. Oops, that was going to autocomplete there for me. Parameters. Set our learning rate. LR equals 0.001. Momentum equals 0.9. And we are having a small error. No FC3. And that's super easy. Why? You can see. Gotta put our linear over here. So hopefully that solves that, and it does. I'm distracted by those fireworks outside. All right, now let's build out our training loop. So what I'm gonna do is build out this training loop, and then I'm gonna pause this video and I'll come back once this loop trains, because it is gonna take a little bit of time. So first, you set up your number of epochs. I'm gonna do 100, because we want to get a pretty good accuracy on here because it deals with our leaderboards. So I'm going to do 100 rather than something low like 5, 10, or 25. I'm also going to set up a running loss. 0.0. And now let's build this training loop. So for epoch in range, set your number of epochs, right? So 0 through 100, and colon for I and data in enumerate train loader 0 inputs labels data inputs labels inputs dot to device like that labels dot to device. Okay, optimizer dot 0 grad like that. Outputs equal model. Say inputs dot float. Then what we'll do is loss goes criterion defined our outputs and labels, right? Loss dot backwards. Then we're gonna do or backward, not backwards. Then we're gonna do optimizer dot step. And finally, we're going to calculate running loss. So running plus equals loss to item, because we don't need it to be tensor anymore, just numeric value for that loss. We're going to say if I by 100 equals 99, print here, and I'm just going to essentially copy and paste what I had for my print statement just so I don't mess that up. But essentially what I'm printing is the epoch plus 1, I plus 1, and our loss, running loss over here. Just feel like I'd mess this up. And then we're going to do running loss equals 0.0. And then outside over here, once this is done, we can print over here, training finished. Okay, so let me kind of explain some of this code. So epochs I talked about, right? Running loss. Essentially, we're doing batches to go through here. This goes back and over here, our batch size 64, train data loader. All right, so we're batching this. So inputs and labels, right? We're grabbing that. We're just saying those to devices. 0 grad, very popular. Well, you need it. I shouldn't say very popular, but you need this in your training loop. Outputs equals model, input to float, our loss, right? The criterion between outputs and labels, backward step, always needed. And then we're going to continue summing this up. So I am going to run this. If we have no errors, it's going to start printing stuff down below. And I will be back in the video once this continues to go through. So you can see our first one over here, 2.301. But this is going to take quite a bit. All right, I'll be back. All right, so it's been a while, and we reran this. So I did changes back into my GPU, and you can see the loss. We're getting a pretty low loss, right? 0.005, 004. Not too bad. Maybe it could be a little bit better if I had some more epochs, but it's all right. So now what we're going to do is build out our file for submission. So what I'm going to do is put model.eval, and then I'm also going to do is predictions. And this is just the format that I saw someone else did in this competition. So essentially we're going to be doing the same thing. So with torch.nograd here, we're going to say for data in test loader, let's see, data equals data dot to, and we'll put our device in here. And we're going to say outputs equals model data. Then we're going to say underscore over here, predicted equals torch dot max outputs dot data 1 predictions dot extend predicted CPU dot to list. Okay, we're moving our predictions back to the CPU, and I think now we create our submission file. So submission is pd dot data frame, and first thing we're going to do is our image ID. It's going to be range. I'm going to say 1 predictions here plus 1. I'm going to put a comma, and then we're going to say label, and then we're going to put predictions like that. And finally, we're going to say submission to CSV predictions, and let's put our file name over here. Predictions. You guys are going to be watching this in 24, but it is 12:31 right now, almost midnight, and we're going to say 12:31 final.csv, and we don't need an index, so we can say index equals false. And hopefully this works over here. Should. And we'll refresh that. You can see we have our 12:31. So I'm going to download this. So download that. Then what I'm going to do is go back to our competition. Right. So let me do that. Be back in a second. And we're going to submit this prediction. So you go over here to submit prediction. So you can drag and drop your file. I'm going to drop that over here real quick. So you can enter your description if you want. I'm going to click submit, and let's see how we have our final score. And 0.988857. So not a horrible score. My best was 0.98942, I think, or no, this one was. So not a horrible score, although I did have a 0.9846, but you can see a leaderboard over here. Some people obviously cheated having this perfect score, but right now my score is 467, and like I said, over here was 9857, but that was my best one, so pretty close to 99%. It rounds up, and yeah, that is it for the Digit Recognizer. Hey, this is the end of the video, and you made it. Congratulations on that. I know this isn't the easiest source material out there. If you were able to learn something or even build out this Kaggle project, all I ask for is a subscribe. And if you have other friends that are studying data science, make sure to share this video to them. That way, this YouTube channel can continue to grow. These videos do take quite a while to make, and I do appreciate it. Now, I do have some other data science videos right over here, so you should go check some of those out.